Cool. Let's zoom in a tad. Okay, awesome. So hello, friends. How are you guys doing today? That is fair. Okay, so last time, basically to summarize, we started molecular orbital theory, and I wanted you guys to have some time to like stew, because I know it can be one of those topics that's like either super straightforward or super complicated. And all we did last time really was 1,3-butadiene, and we did the drawing for it, and we talked about the ground state and the excited state. So today, we're going to go through the other 3 examples that are on my handout up here. And we're going to fill out this table, which I'm just going to right quick erase because we're going to fill that out together. I forgot to do, oh my gosh, please. Okay, cool. So before we move on, there was one thing that I forgot to show you guys. So I am going to draw it out for you. And then if it makes no sense to you, you can completely ignore it. So for a quick second, I'm going to erase this. And last time we talked about how this is the lowest energy level, and then as we move up, we go higher in energy, right? And so basically, a way we can depict that is by drawing out the orbitals. So next to each line, I'm going to draw out 4 orbitals because that's how many we have. And at the lowest energy level, we're going to color in the same side. So all of these guys are going to be colored in on the same side. And then each time we go up an energy level, we're going to introduce a node. And that node is basically a spot where the coloring switches sides. So up here, we're going to have 1 node, and I'm going to put it in the middle. And that means we go from up to down. And this flip means that it's higher energy. So that's why this orbital is higher energy than the one before it. So then the next orbital is going to have 2 nodes, and I'm going to put them like that. So color in the top, switch, and then color back the top because we switch. And then the highest energy level is always going to have a node between every one of the orbitals. So we're going to switch, switch, switchity switch. Yes. You wouldn't, this is purely just so like you understand the theory behind it. Yeah, exactly. And the node thing is going to be sort of kind of important for the, not really, but it'll help you understand something for the next one. That's why I introduced it. So yeah, that's pretty much all there is to it. If that's wildly confusing to you, don't worry too much about it. But yeah. Have fun. Okay. Okay, so next we're going to do the allylic cation. And I'm just going to move this down a tad. I wish I could spell. Okay, so before I draw out the cation, I want to make a note. So sp2 can be double bonds, but it could also be cations, anions, and radicals. So what this means is this carbon right here, since it has a plus charge, oh, I'm so sorry. I don't know why the palm rejection is being dumb today. So that positively charged carbon, even though it doesn't look sp2, it actually is going to have a p orbital. So we know that each one of these carbons in a double bond has a p orbital, and now we know that the cation has a p orbital. But since it's plus charged, there are going to be 0 electrons in there. And there's going to be 1 electron in each of these because those carbons are part of a double bond. So how many atomic orbitals do we have? 3. How many molecular orbitals do we have? 3. How many total pi electrons do we have? Ooh. 2, yeah, there's 2 electrons because there is a cation. This last This last p orbital is empty. So it's going to be 2. All right, so now when we're drawing the lines, we're going to have 3 energy levels. 2, 3, right? We have pi 1, pi 2, pi 3. And let's just draw out this thing. So at the top, and then we know we're going to introduce a node, right? The weird thing that happens here is the node actually goes right where this middle orbital would be, and it cancels it out, so we end up having only 2 orbitals. And then in the 3rd energy level, it looks normal again, and we flip at each one. Why am I telling you this if you're not going to be asked about it? Well, this becomes something funky, and you can either think about it in the scientific way or the Rosemary way. So we're going to cut this in half to figure out what's bonding, what's anti-bonding. So we know that everything under the line is what? Bonding, and everything above the line is anti-bonding. But now we have something on the line. And that's going to be non-bonding, exactly. And the scientific reason it's non-bonding is because there's no orbital in the middle. We have the node that replaces it. So whichever of those 2 ways makes more sense to you, that's how you can think about it. Does anyone want me to repeat anything? Yes, this the whole thing? Oh, okay. Yes, exactly. So the question was, is there only non-bonding orbitals when it's an odd number? Yes, exactly. So the only reason it's non-bonding is because, again, the number of bonding and anti-bonding have to match up. So whatever's left over in the middle, that's going to be non-bonding. Yes, Leah? Yes. No. They're just going to go up 1 energy level. But when they're there, you can't do anything with them. Yeah, for the purposes of this class, they're going to. Exactly. I know it's a weird, I know, yes. Yeah. So it would be like, let's say we have 1, 2, 3, 4, 5. Again, we're going to cut it in half. So pi 1 and 2 are bonding. 3 and 4 are anti. And so still this one single one in the middle would be non-bonding. For this class, yes. Okay, so let's distribute some electrons. We're going to say 1 and 2. So if we only have 2 electrons, we are only filling up the pi 1 orbital. What is our HOMO? Pi 1, because why? Yes, so HOMO means highest occupied orbital, so it's the highest number that has electrons. And so then what's the LUMO? Pi 2, and why is that? Yes, this is the lowest orbital without any electrons in it. Cool. All right, and so just, I wish I wrote this before, but this is the ground state, right? If this were to get excited, what's the only thing that's going to change? Yes, so hold on, I'm just gonna copy this. duplicate, put it over here. All right, so as everyone was saying, the only thing that would change is we move one of these electrons from the HOMO up to the LUMO. So this is excited. And again, just to reiterate, the difference is one electron jumps from HOMO to LUMO. Yes. Question? No. Okay. Okay. Yes. Perfect question. So HOMO is the highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital. And just to repeat something that students find very confusing, but we talked about last time. So the HOMO and LUMO we define in the ground state. We do not change that in the excited state. So even though there is an electron here, this is still the LUMO, because remember, the excited state is just a temporary state. It only lasts for like a couple seconds at most. So we're not going to change these labels. We're only going to throw the electron up and then jump back down. Yes. What do you mean? Ask me that after, and I will nerd out and I will show you. But I don't want to confuse everyone because that's way beyond the scope of this class. But if you ever wonder, I can send you some cool drawings. Okay, any other questions? Yes. So for the purposes of this class, you can treat them as the same thing. Yeah. Okay. So we are going to move on to the radical, and I actually think that in here, yeah, in these notes, like in this table, I put anion and then I put the radical, but I'm going to go over it in the opposite order. I'm going to do radical and then anion. So please don't get confused. Just make sure you are following what you're, yes, radical. Okay. Sorry if the scrolling is like annoying anyone. All right, so for the cation, anion, and radical, they're going to have very, very similar diagrams. So what I'm going to do, just to make life easier, is I'm going to copy it. So you don't have to sit here and watch me like struggle for an hour. And I'm just going to change very small things. Okay, all right. So this is so awkward. I'm so sorry. The awkward silence is killing me. All right, so we're going to do the allylic radical. And radical means that we have one electron by itself on this carbon, right? So how many electrons would be in that p orbital? 1, exactly. So literally, and I'm going to erase it from here. So literally the only thing we changed from the cation to the radical is we added 1 electron into the mix. So how many atomic orbitals do we have? Still 3. How many 3? How many electrons? Now we have 3, exactly. Okay. So when we're filling it up, 1, 2, gasp. There's 1 electron all by itself. Is that stable? No, that's why radicals suck. We hate that, right? But now this puts an interesting question. Which one of these is the HOMO? It is pi 2. So something students will assume is it has to be the highest completely full orbital, but that is not the case. The HOMO is just the highest number that has any electrons in it. So then what's the LUMO? By 3, yay. All right, so where am I taking an electron and where am I putting it in the excited state? 2 to 3, exactly. Oh, I don't know why I did that. So we're gonna have 1, 2, empty middle 1, 3. Coolio. And that's pretty much the only difference between the allylic cation and the allylic radical. Let me just write HOMO and LUMO just so that stays. Any questions about the radical? Bless you. Okay, so I will just zoom out a tad so you can see both at the same time. Any questions like comparing and contrasting the two? Yes. So that's going to stay exactly the same because that only changes when you change the number of energy levels. And since we only have, since we still have 3 pi orbitals, excuse me, 3 p orbitals, this diagram that I drew and the number of bonding, non-bonding, anti-bonding, that's not going to change. So remember, the labels are not going to change. Oh, I see what you mean. Okay. It's still non-bonding because of that like node in the middle that cancels out the middle orbital. Yeah. It's really weird. I know. Just it's one of those things that if I explain it anymore, it'll make you more confused, but it's not the best answer right now. Yeah. Yes. Yeah, of course. Yeah. Here, I'll zoom in a tad so you can see that. Bam, bam. Just let me know whenever you're done. Take your time, but it makes a weird sound. Don't judge me. I'm the baby. Does anyone here know who Elijah she's a comedian, she's blonde. No, never mind. Her hair has changed a lot throughout the years. I don't think that's the one though. I think they're very similar. But anyway, the whole thing is she has like a bit where she talks about her dog and she just goes, "Who's the baby?" And I quote that all the time, but nobody gets it. So, you know, why would you, right? I don't know, bro. The Ice Age movies felt like a trip. Like this, yeah. I feel like I watched those movies like no less than 10 years ago, and I don't know what happened in any of them. Right? It is. It's so weird. Yeah. Yeah, exactly. Hello. Yes. Yes. You should watch her videos. She's really, really funny. Yes. Evelyn. That's your name. There we go. I knew there was an Evelyn. Okay, I'm not losing my mind. Yeah. You're just that special that everyone else is like, yeah, you should. I'm kidding. Okay. Are you good? Are you still working on it? You good? Okay, cool. So let's do the last one, which is, excuse my bad accent. Next up is the anion. Very good. Okay, so again, bonding, non-bonding, anti-bonding, all that kind of stuff is staying exactly the same. But now we have an anion. So anion means what charge? Negative. So negative means how many electrons? Okay, yes. I thought you meant like on one carbon, and I was like, do we have to go back a little bit? No, so what we're gonna do is we're gonna draw 2 electrons here because it's a negative charge. And like you guys said, you're absolutely correct. It'll be 4 total electrons, and the number of orbitals does not change. So I'll fill that in. Yeah. So now when we go to, yes, question? Okay, so just a little recap. This one, we're doing the allylic position, and we're doing the cation, anion, and radical. And so we know that there's going to be 1 p orbital for each of these carbons that are part of the double bond. And then we're going to have a p orbital here because anions, cations, and radicals are actually going to have p orbitals. So for that reason, it's 3. Yay. Okay, cool. Am I that boring that you keep yawning? I feel that. Sometimes I try to like pretend that I'm like threatening, like I'll say something like that, and then everyone just looks at me like, shut up. Yes, my sippy cup water bottle. Okay. Anyway, when we put the electrons in, hold on, it's taking a moment. There we go. So we're gonna have 1, 2, 3, 4. Wow. So, yeah, there we go. So my question was going to be, where does the electron jump? It jumps from 2 to 3. Yeah, it could be either way. I'm going to redraw that because that's ugly. There we go. Yes. So, okay, for a second, I was like, I just was like zoned out. Okay, so what is non-bonding? For the purposes of this class, we're going to say non-bonding is going to be the one in the middle if we have an odd number of orbitals. So when you make that line to decide bonding and anti-bonding, if there's an orbital on that line, we're going to call it non-bonding. Okay. Any questions, comments, concerns? Yes. Yeah. Exactly. And the reason for that is because there's an even number. So if there's an even number, there's going to be no non-bonding. You're so very welcome. All right, so I'll give it another moment. Yes. Oh, that's what I forgot to ask. Yes, so HOMO is going to be pi 2 still. LUMO is going to be pi 3. Good point, thank you. Yes. Yeah. So just in case anyone didn't hear, the only examples of sp2 that you have to know in this class are double bond, cation, anion, radical. Excuse me. Yes. That would be sp, not sp2. Which, beyond the scope of this class, but you actually could put a triple bond in here because it does have a p orbital. It's just, yeah, never mind. You don't want to know. Any questions? Everyone looks so tired. Yeah. I feel that. I feel that. You know what we're going to do? Okay. We're going to move on. Cool. Okay. So the next up on our list, I don't know why we didn't do this question the other day, but I guess it's a good little review before we totally move on. So which of the following would have a UV absorption at the longest wavelength? So when it says longest wavelength, are we looking for more or less conjugated? More, yes. So how many bonds does this have in conjugation? Ah, there's 3. 1, 2, 3. We want more. Yeah, long wavelength means more conjugated. Yes, I can. So we have, I know it's weird in the condensed-ish formula, but we have 1 double bond, 1 single bond, 1 double bond, 1 single bond, 1 double bond. So it says 3 in conjugation. How about the second one? Only 2. These are in conjugation, but this one's all the way over there by itself. So it has 3 double bonds, but only 2 of them are in conjugation. Next up, how many do we have here? Can you have 1 double bond and be conjugated? No. So this one has this double bond here, this one here. They're way too far apart. So this has 0 double bonds in conjugation. So this is not conjugated at all. What about the last one, or second to last one? 2. Again, these 2 are conjugated with one another, but this one is too far apart, so it doesn't count. 2. And now, for real, the last one. It's the same molecule. Cool. So these are in conjugation. The third one is all by itself, so we only have 2 in conjugation. Let me just make sure. Yeah, there we go. So which one of these guys has the most conjugation? Number 1. Yay. Go team. Any questions on this? Yes. Yes, so we will go over the trend one more time because I know someone else is also thinking that. So higher conjugation equals lower energy equals longer, I'll do arrows for everyone, longer wavelength, low frequency. Yes, what's up? Absolutely. So just to reiterate, based on this, that means number 3 would have the lowest or the shortest wavelength because it does have the least amount of conjugation. Correct. And then 2, 4, and 5 would all be tied. Cool. So I'll take a sip and then I'll move on. Look. Oh, okay. Now to the fun stuff. We're doing a reaction. Yay! I think it's fun. You guys probably don't, but it's fine. We're gonna have a good time. I was totally in class today, but I'm just going to, test you guys. What did you do in lecture today? Kinetic? Okay, so yeah, you finished. I love being on top of my game accidentally. Okay, cool. So we're going to do something that you might have started a tiny bit. I don't think anyone here is from Roche's class, but, huh? Roche? I said Roche. Back to the thing. Okay, so we're going to call this reactions of conjugated systems. We can also call it 1, 2, 1, 4 reactions. And as always, I don't give myself enough room, so I'm going to make a new page. And I'm going to show you guys a reaction. Yay. Let me just make sure this is what I have. Yeah, okay. Bam, bam. Yeah, stop yawning. You're making me tired. Okay, so in an addition reaction, we're going to have a nucleophile and an electrophile. And nucleophiles do what? Attack. Awesome. So here we have two options. We have this guy, we have this guy. Which one do you think has a possibility of attacking? And it's going to be the double bond. So the double bond has extra electrons, right? So it can use these electrons to possibly take a hydrogen. So did that act like a nucleophile? Kind of. No, it is going to be a nucleophile. It's not like what you see usually how nucleophiles look. It looks more like a base, right? Because all it did was steal a hydrogen. But in this case, we do call it a nucleophile. And now we're going to have a double bond replaced. We're going to add a hydrogen somewhere. Are we going to add the hydrogen to the more substituted side or the less substituted side? Okay, so we got some, like really good questions. Is it Markovnikov? Maybe we could do both. So we are actually going to do Markovnikov. It's not, yeah. Basically in Orgo 2, every time it's going to go to the less substituted side, and the other group, the more important one, will go to the more substituted side. So you can think of everything as Markovnikov, unless I specifically tell you otherwise. Okay, so now what do we have here? A carbocation. Cool. Okay, so now that we have a carbocation, and we also have Br minus, what can we do? Attack. So the Br minus can attack the, I don't like that arrow. Bam. So we're going to add a bromine right where that carbocation was. So we end up with an H here and a Br here. Yeah. Okay, so yes, what's up? It is an addition reaction, yes. Okay, so what do I mean by 1, 2, 1, 4? This is another thing that students get very tripped up about. So when I say 1, 2, 1, 4, 1 anything, when I talk about numbers, I'm not talking about like IUPAC naming here. I'm talking about where things were added in relation to one another. So the hydrogen is always 1 because that's the thing that was added first. So 1. And then where was the bromine added in comparison? 2. So their relationship is 1, 2. So this is the 1, 2 product. And I can repeat that one more time. So since the hydrogen and the bromine were added in relation 1, 2 to one another, aka adjacent, this is going to be called the 1, 2 product. Yes. Yes, exactly. So HBr is the electrophile. This guy is the nucleophile. It just gets attacked. Yeah. I did. So we could have done something else here instead of this reaction. So when we have a double bond, what can we sometimes do with it? Resonance, exactly. So I'm going to do the resonance in purple. So instead of going forward, we could have done a different mechanism, which would have been moving this double bond over. And that would have made our intermediate look, wow. Big, I'm going to leave it. I'm going to leave it. Sorry, don't sound so disappointed. Oh, okay. So we still have the hydrogen added here. And now our plus charge is all the way over here. Yikes. So we still have Br minus in this case. And so instead, Br minus would attack this carbon. And so we would add a hydrogen. Oh, excuse me. The hydrogen would not move. It would stay in the same spot. And we would add the bromine all the way over here. So we get Br, we get H, and we get a nice little double bond right here. So let's finish this up and then I'll show you what the questions might look like. Okay, so let's start counting again. 1, because the hydrogen was first. 2, 3, 4. So their relationship to each other is 1, 4. This is the 1, 4 product. Yeah. Oh, yeah. No, what? Sorry. Okay. I just lost the one brain cell that was firing. Okay, cool. So what you're saying is actually like the next step that I was going to talk about. So when we're talking about mono-substituted, di-substituted, whatever, we're talking about the double bond, right? And we have to think about stability of double bonds. So this is something that he actually has a really good picture of in one of his PowerPoint slides. It's like the order of stability of double bonds. And in general, you should know that the more substituted a double bond is, the more stable it is. So in this case, which double bond is more stable, the 1,2 product or the 1,4 product? 1,4, because this one is, tri-substituted. This one is only di-substituted. Yeah, so this one is more, sorry. This one is more stable, the 1,4 product, because it's tri-substituted rather than this one that's di-substituted. All right, we have 4 minutes. I'm going to try to squeeze it in. So we're going to talk about kinetic and thermodynamic. So the kinetic product and the thermodynamic product, I'm going to go over it in a very specific way. And I want you guys to remember it in that very specific way. So we are always thinking in terms of lower. So just write that down and then we'll talk about what that means. Lower, yes. So the kinetic product has a lower, or I'll say lowest activation energy. Whereas the thermodynamic product has the lowest potential energy. The opposite is not true. The kinetic product is not necessarily the highest potential energy, and the thermodynamic product is not necessarily the highest activation energy. So only think in terms of lower energy. Kinetic is the lowest activation energy. Thermodynamic is the lowest potential energy. So what the heck does that mean? Well, lowest potential energy means that you have the most stable product. And lowest activation energy means that it's easier to make product. So we can say it's faster / less steps / requires less energy. We're also going to say that thermodynamic is favored in high temps and kinetic is favored at low temps. And we can talk about this a little bit more next time. But so based on this information, we're going to assign kinetic or thermodynamic to the 1, 2, and 1, 4 products. So let's start with lowest activation energy. How in the world could you tell lowest activation energy just from this reaction? Why? Yes, okay, so the 1, 2 product is going to be the kinetic product because it happens 1 in the shortest number of steps, and 2, it has the more stable carbocation. So I'm going to say this is kinetic. So again, it's kinetic because it has the lowest activation energy, because it happens in fewer number of steps, and it has a more stable carbocation. Now, in this case, this is not also the thermodynamic product, but I don't want you to look at every single one and be like, oh, okay, one is kinetic, so the other one has to be thermodynamic. One product can be both at the same time. In this case, that's not true. We'll talk about that more next time. But in this case, 1, 4 is the thermodynamic product. Can you tell me why? Yes, exactly. So it's the thermodynamic product because it has a more stable double bond. And that's how you know it has the lowest potential energy. So just to recap, if we attack the hydrogen, form our carbocation, and immediately add our bromine, we get the 1, 2 product, which ends up being the kinetic because it happens in fewer steps and it has a more stable carbocation. If we end up doing resonance and making a less stable carbocation, we get the 1, 4 product because we add the bromine all the way over here. And that ends up being thermodynamic because this double bond is more substituted, therefore it is more stable. And we know that the kinetic product is always lowest activation energy, and the thermodynamic product is always the lowest potential energy. Questions? Yes. Ta-da. All right. I will stick around for any other questions. If you don't have any, have a wonderful day, and I will see you Friday, maybe. I mean, if you guys want to come, I'll be here, and I'll have stickers for everyone, so. Oh. I'm sorry to anyone.